Section 5.4, indefinite integrals and the net change theorem. Right, so this section, I think, tends to go pretty well because it's actually going to talk about something we've already dealt with back in chapter 4 when we talk about finding antiderivatives. Right? And so now that we have that connection between the antiderivative and the integral, right? So evaluating an integral then ultimately, like I said, is nothing more than finding the antiderivative of our integrand. And in this case, we're dealing with indefinite integrals, so we're not using or putting limits of integration on this thing. Right? So at least not initially, then we'll talk about the net change theorem and what that's all about, but that's going to bring in a definite integral, but in the context of finding change in position. Right? So we'll get to that. Excuse me. So we'll take our indefinite integral, say the integral of little f of x dx, all right, being equal to the antiderivative of little f, which we can call cap f of x, right, which means, of course, then that cap f prime of x equals little f. Now, like we talked about previously with finding those general antiderivatives for an indefinite integral, right, we're finding the antiderivative, the general antiderivative of little f, which is going to be cap f of x plus c. All right, so whenever we're finding those general antiderivatives, no limits of integration, indefinite integral, we've got our antiderivative and always tacking on that plus c, that arbitrary constant. All right, so don't forget that it'll happen, and that's a deduction because like we talked about with antiderivatives, if you don't put the plus c, then you're only giving me one antiderivative out of actually an infinite number of antiderivatives. So for example, the integral of x squared dx, right, there's our power rule, x cubed over 3 plus c. Okay? And remember also too, we said when we're finding these antiderivatives, you can always check them by differentiating, right? If you differentiate your antiderivative, then you should end up back with your integrand, right? So x cubed over 3, the derivative would be what, 3x squared over 3, which leaves us with x squared, and then the derivative of the constant is 0. So you can always double check your integrals, you can always double check your antiderivatives by differentiating. Now the definite integral, when we put limits of integration on there, as we did in the previous section, that's a number, right? We can actually calculate a value for the integral by plugging in the upper limit and then subtracting the antiderivative evaluated at the lower limit. An indefinite integral, as we said, is a function, right? Actually, it's a family of functions because, like I said, the arbitrary constant, the plus c, gives us an infinite number of antiderivatives, right, in the general form, but it's a function nonetheless, right? So a definite integral is a number, it's a value, we can find it, we can calculate it. An indefinite integral is a function. Page 403, just for reference, there's a table on that page that gives you some indefinite integrals that we've kind of already mentioned that you should be familiar with. All right, so that's a little reference page for you. And then the next example, like we said above, you can always verify an integral, or in this case, we're going to verify that the following formula is true. Now this goes back and talks about, remember we did the properties of integrals, and we said the integral of a sum is equal to the sum of the integrals. It was also true for subtraction. But we did make the note that it's not true for a product. So in other words, the integral of a product is not equal to the product of the integrals. So here's one little example to show that that is the case. So we're asked to verify this statement. We're saying that the integral of x times cosine of x dx, right, that's a product, is equal to not just the antiderivative of x times the antiderivative of cosine x, but it actually is equal to x sine x plus cosine x plus c. So there's a lot more to it, obviously. Now, dealing with these, so I'm not asking you to integrate this thing. We're asking you to prove that this or show that this statement is true. So we're saying that this is the antiderivative. And let's prove it. How do I prove it? How do I show it? We find the derivative of that. All right. So finding, and I mentioned this before, I think, with you, finding antiderivatives of the products, integrals of products. That's something you're going to look at in Calc 2 if you're heading into Calc 2. That's one of the more, difficult, more involved processes. Right? There's a whole process involved for working with products, and there's a lot of other processes that you're going to talk about in Calc 2 that we're not going to get into in Calc 1. And so it's your first part of Calc 2, which deals with integration methods and are finding antiderivatives for all these cases that are a little bit more complex. All right, so let's show that this is a true statement. How do I do that? I differentiate the antiderivative. All right, so we differentiate x sine x. Always have the wrong marker. So we differentiate x sine x plus cosine x plus c. Now, we're back to basic differentiation. Don't forget everything you know about finding derivatives. We're not done with the derivatives yet. We're never done with derivatives when you're talking calculus, but and so don't forget how to differentiate. So recognize x sine x is a product. So I'm differentiating using product rule here. So our first d seconds, so our first is x times the derivative of sine is cosine, plus the second, which is sine, times the derivative of x, which is 1, so I'd have just sine. And then plus the derivative of cosine is negative sine, so minus sine. And then the derivative of our constant is 0. And so we do end up with x cosine x plus sine x minus sine x, which leaves me with just x cosine x, which is our original integrand, right? So if you find an antiderivative and then you differentiate it, you should get back to the integrand, which we do in this case. So that proves that that is a true statement. All right, so you'll see a few of those in your homework. The rest of these are integration. All right, so actually finding antiderivatives, but again, really we only have a few different cases that we can work with at this point using our power rule for finding antiderivatives. We can work with trig functions to a certain degree. We can also integrate our e to the x. Right? We know the antiderivative of e to the x is e to the x. So, but again, we're still just working with a few cases. But just like when we were finding derivatives of functions, in some cases, the first thing we did was actually rewrite the function into a different form or into an equivalent form by simplifying, or in the case of trig functions, you can use identities, this kind of thing, to rewrite the function into a form that you could actually then differentiate, using one of our known processes. Well, the same thing happens with integration. When you're finding an antiderivative, if I have a function, my integrand, that is not in a form that I have a process for directly finding its antiderivative, it may require some rewriting of that integrand, whether it be a simplification or a rewriting of it in some process using identities in the case of trig functions that ultimately gets my integrand into a form that I can actually find the antiderivative of using one of our known basic processes. Right? So that's going to be part of it as well, just like with derivatives. So number one, I've got the integral of x squared plus 1 over x squared plus 1. Now, property of integrals, like we said, the integral of a sum is equivalent to the sum of the integrals. You don't have to break it up like that. I mean, the same thing was true with derivatives, and we didn't bother breaking it up term by term. We just did it. We found the derivative. So the same thing is true for integration. So you don't have to rewrite it as I have there. You can integrate term by term, but you may find in some cases it's helpful to do that, because I think integration, generally speaking, tends to be a little bit more of a challenge than differentiation. Right. So if you find it helpful or useful to break it up term by term, then do that. But if you can get it done without that, that's fine. But we've got the antiderivative of x squared, which is x cubed over 3. That's again a basic power function, power rule. Increase the exponent, divide by the new exponent. The antiderivative of 1 would be x. And then the next one is one that we have to recognize. Remember, I told you this when I mentioned these previously, that the authors of this textbook tend to throw in this inverse tangent from time to time, especially, right? But you need to remember that, or recognize the derivative of your inverse trig functions. So the integral of 1 over x squared plus 1, its antiderivative is inverse tangent of x. But again, that's just pure recognition. And then we tack on our arbitrary constant, right? So don't forget, always tack on a plus c when you are evaluating an indefinite integral. Next one, number 2, is a prime example of using trig identities. Right? So some of those basic trig identities we may have to remember and recognize. The double angle identity for sine is 2 times sine times cosine. Now, some of you get very creative when you're trying to simplify fractions. Don't violate all the basic rules of algebra when you're simplifying a fraction. This is the sine of 2x over the sine of x. I can't just divide out the sine because the arguments are not the same. I can't divide out the arguments, 2x and x. I can't just divide out the x because those are the arguments of trig functions, not factors. Don't forget, don't violate basic rules for simplifying fractions. So what I did in this case was I said, well, I really can't do anything the way that's written. I mean, there is no quotient rule, just like there is no product rule. I can't just break it up and find the antiderivative of each of those. So, like I said, a lot of times with trig functions, you're going to have to make use of some basic identities to rewrite and simplify or rewrite into an equivalent form. So in this case, if we use our double angle identity for sine, rewrite that as 2 times the sine of x times cosine of x over sine of x. Then we're able to divide out the sine of x, and I'm left with 2 cosine x. So I've got the integral of 2 cosine x dx. I've got that now in terms of a single trig function. Now you also have a constant here, and again, when I talk about the properties of integrals initially, and we talk about the constant multiple rule, the fact that if you have an integral of a constant multiple of a function, right? So if your integrand is a function times a constant, you can pull that constant out of the integral. And I mean, probably in this case, not such a big deal because we're not dealing with a very complicated integrand. But you may find that helpful as we go further. All right, as your integrands get a little more interesting, that if you can get that constant out of the way, it may just make it a little bit easier to see what you need to do with your integrand in order to find its antiderivative. So, but again, whether or not you do that, that's just, do it if you need to. If you can do it without it, that's fine. So what I did, the next step, I went ahead and pulled the constant out. So I've got 2 times the integral of cosine of x dx, and our antiderivative of cosine is sine. So I've got 2 sine of x plus c. Always plus c for an indefinite integral. Number 3, I've got the integral from 0 to pi over 3 of sine of theta plus sine theta tan squared theta over secant squared theta. All right, so I know how much we do love our trig functions. But I think pretty standard with a lot of these integrands involving trig functions, there's going to be some rewriting, So you're going to have to, again, recall some of your basic trig identities, but at least initially in this case, I'm rewriting the numerator in factored form. I'm able to factor out a sine, which leaves me with 1 plus tan squared over secant squared. And so here's the recognition that that's one of those Pythagorean identities. 1 plus tan squared is equal to secant squared. And that's the key to this one, because without that, I wouldn't be able to rewrite or simplify this into a form that I could work with. So here then we're able to divide out the secant squared, and I'm left with the integral from 0 to pi over 3 of sine theta d theta. Now, antiderivative, and we talked about this back in 4.9 when we were dealing with initially, finding antiderivatives of those trig functions. Watch your SIGNs when going from sine to cosine and vice versa, all right? Because the derivative of sine is cosine. But the antiderivative of sine is negative cosine. Why is that? Well, what if we differentiate this? What is the derivative of cosine? Because remember we said I can always check by differentiating my antiderivative. What's the derivative of cosine? The derivative of cosine is negative sine, not sine. So to get that, I need to tack on that extra negative. Okay? That's the easiest way to double check that. And don't forget that. I mean, so, just to make sure you have the correct SIGN, positive or negative, on these antiderivatives, especially when you're dealing with these trig functions, once you find your antiderivative, you just do a quick differentiation to make sure your sign is correct. And if you're off by a sign, if you're off by a negative, then just tack on that negative onto your antiderivative, and that'll fix it. So our derivative cosine is negative sign times that negative does give me a positive sign. And then we're evaluating that from 0 to pi over 3, so there's our basic trig function values again that we keep mentioning. I've got the negative cosine of pi over 3 minus the negative cosine of 0. Cosine of pi over 3 is 1/2, so I've got negative 1/2. Cosine of 0 is 1, that's minus negative 1, so plus 1, which then gives us 1/2. Now the base of the calculations there, that's on you. All right, you're knowing your basic trig function values. And then obviously the calculations with the values themselves. Number 4, another, straightforward example of rewriting first before I can integrate. So the integral from 1 to 4, 2x plus 5 times 3x minus 1 dx. And also too, while I'm thinking about this, anytime you write an integral, you better include that dx. Right? Don't give me an integral that doesn't have a dx, because that means nothing without the dx. And that's one of those things, again, I think we just kind of, we get lazy, for lack of a better word. We just get lazy with the notation, but I keep harping on that notation, notation, notation. So integral from 1 to 4 of that product of binomials dx, but again, we don't have a process for integrating a product. Not yet. But this is easily resolved in this case because I can multiply those two out. I can use the fall method, right? And rewrite this then as the integral. So here's our original product. So I just got the integral from 1 to 4 then of 6x squared plus 13x minus 5 if you multiply those two together. And now we're back again to using our basic power rule, right? So antiderivative of 6x squared, 6x cubed over 3. Antiderivative of 13x, 13x squared over 2. Right? Power rule, increase the exponent by 1 and then divide by the new exponent. Antiderivative of 5 is 5x, and also a reminder, be careful of which direction you're going. Because like I said, we're not done differentiating stuff yet. And it's easy to get caught going the wrong way with that. So just be careful. Am I finding an antiderivative, power rule, or am I differentiating using the power rule? And then I just went ahead and simplified that first. So I'd have 2x cubed, 13x squared over 2 didn't change, but then, so it's just simplifying of the 6x squared over 3 to 2x cubed. And then we're evaluating that from 1 to 4. So I went ahead and plugged in the 4. Minus, plug in the 1, and ultimately I've got 208.5. Right? So again, reminder, what do I need to see from you? Obviously, I need to see that antiderivative. Right? So the integral of our integrand, our function, what is the antiderivative? Evaluated from what to what, from A to B. And then I at least need to see those numbers plugged in. Right, so show me that you're plugging in the upper limit minus the lower limit. Okay. But like I said, you don't have to show me all the little calculations. You can show me your final result, and that's fine. Okay. But again, really nothing new there. I mean, other than just mentioning the fact of how we need to rewrite those integrands using some basic processes so that we can put it into a form that we can actually find the antiderivative of. All right, application, and this kind of goes back to something we talked about earlier. When we talked about particle motion, we talked about displacement versus total distance traveled by an object, that kind of thing, and how those were different concepts. We had a whole section where we did an application, right, where we found velocity and acceleration and where the object was moving forward and backward. Right? Remember, positive velocity, we're going forward. Negative velocity, we're going backward. So this application is going to be kind of similar to that, but it's putting it now in the context of the integral and how if I'm taking the integral of a velocity function, then I'm finding the antiderivative of the velocity, which is position. And I can calculate the change in position of an object over a given time interval, in this case now knowing the velocity function. Okay. But then also, again, remembering that there's a difference between distance traveled and displacement. Okay. So first, we're calling this the net change theorem. The integral of a rate of change is the net change, because like we said, even when we're talking area under the curve, if we said the integral from a to b of cap f prime of x dx would be its antiderivative, cap f evaluated from at the upper limit minus the antiderivative at the lower limit. But remember we said geographically this represents the area under the curve, but it's not the total area, it's the net area, right? Because maybe some of the area is above the x-axis, some of the area is below the x-axis, and so we said that represents net area. Well, the same thing would be true in terms of velocity and position. So if I take the integral, say from time 1 to time 2, whatever our time interval is, of a velocity function, v of t dt, then I find the antiderivative of our velocity function, which is our position function, which we typically call s. I evaluate that at t2, at our upper limit, minus that position function evaluated at the lower limit, t1. And that's going to give us the displacement of our object, or we could say the net change in its position, right? Now, if I want to know the total distance traveled, and this, again, I think this was back in section 3.7, if I remember off the top of my head, we said we could actually calculate the total distance traveled if we first figure out where the object changed direction. So was it traveling in a positive direction? And then it changed direction and traveled in the backwards or negative direction, right? And then we could calculate the distance traveled over each of those intervals and add them together as positive values, or we use the idea of absolute value there, to give us the total distance traveled. But in order to do that, we first have to determine where that object changed direction. Remember, how did we determine where the object changed direction? What did we do? We found where the velocity was 0. And so if we find where the velocity is equal to 0, then those then are the potential locations of change of direction. We can also determine where velocity was positive or negative once we do that. And so then we would know where the object was traveling forward and where it was traveling backward. And then we should be able to calculate the distance traveled over each of those time intervals to give us the total distance traveled, right? So it's very similar to what we did before, but in this case we're starting with the velocity function. Whereas previously we started with the position function. We had to find the velocity function, determine where it was equal to 0, and so forth. Here we're starting with the velocity function, which means I then have to find the position function to calculate the distance. So we're just going in the opposite direction. So for example, given the velocity function, in this case we're going meters per second, or units. Please watch your units. Units, don't forget to tack on units, appropriate units when you are working with applications. We're going to find two things. We're going to find displacement of our object, and we're going to find the total distance traveled during the given time interval. All right, so these are two different things. So we're given the velocity function. We are given that velocity v of t, t squared minus 2t minus 8, and we're interested in the over this time interval from t equals 1 second to t equals 6 seconds. So first of all, the displacement. That is nothing more than the integral, right? We said that's what the integral is. It calculates the net change in position, which is what we're calling displacement. What is the position at t1? What is the position at t6? Where did it start? Where did it stop? And what's the distance between the two? So for displacement, that is simply the integral over our time interval from 1 to 6 of our velocity function, t squared minus 2t minus 8 dt. So given velocity, I want to find distance or displacement. I'm going to find the antiderivative of our velocity function. So for our displacement, it's simply the integral. So we find our antiderivative. Again, nice little power function here. So t cubed over 8 minus, that would be 2t squared over 2, so just t squared. And our antiderivative of 8, which is 8t. And then we're going to evaluate that from 1 to 6. And if I plug in 6, I'm going to get negative 12. If you plug in 1, you're going to get negative 26 thirds. All right, so that's our S of B minus S of A, antiderivative evaluated at the upper limit minus antiderivative at the lower limit. And that would then give us a total of negative 10 thirds meters, because remember, what is this? This is distance traveled. Antiderivative of velocity is position. And so I've got negative 10 thirds meters as our displacement. And remember we said that there's a direction component for distance. In this case, if we've traveled a distance of negative 10 thirds meters or negative 3 1/3 meters, then we've traveled backwards from our original starting point, or we ended up, I should say, backwards from the original starting point, right, or whatever we consider the negative direction. Okay. Now, if we want the distance traveled, right? Now, a couple of different notations that you can use here. I don't care which one you use. Because we're talking distance traveled, I'm putting absolute value, notice, on our velocity. Right, because we want all of our distances to be positive distances. So even though we're traveling backward across some of our interval, we know that's the case. I want to calculate that as a positive distance traveled so that I can add it to the other distance on the positive side of our direction to give us a total distance traveled. But we need to know, right, where that object changed direction. So we're going to do it exactly the same way we did early on. We find where the velocity is equal to 0. Now remember, this is the velocity function that we're given, right? So I'm setting that velocity function equal to 0, solve that equation, factor it. In this case, I've got t equals 4, t equals negative 2. I don't care about the negative 2. It's not in my interval. My interval, remember, is from 1 to 6, so I only care about t equals 4. So I know there was a change in direction. Now, you could even go a step further. You can determine where the velocity was positive and negative, right? We do a little test strip like we did. If t equals 4 gives me a velocity of 0. And let me label this, because to remind us again, what are we looking at? Here's my test strip for our velocity function. And so then I would plug in test points, maybe plug in v of 2 if you wish. Which should give you a negative value. Maybe plug in 5 from that second interval. Would give you a positive value for velocity. So we know where the velocity is negative, we know where the velocity is positive. So I know that when I calculate over this part of my interval, I'm going to want to put absolute value on that to make that a positive value so that I can add that to the other to get my total distance. Okay. Now, you don't necessarily even have to know this. You can just simply break the interval into 2 parts, because we know we're traveling in one direction on the interval from 1 to 4. We're traveling in an opposite direction on the interval from 4 to 6. So we're going to have to break the interval into 2 parts. So I'm going to have 2 integrals over each of those time intervals. And then if you put absolute value on both intervals, let me write it this way, so that the integral from 1 to 6 would be equal to the integral from 1 to 4 of our velocity function plus the integral from 4 to 6. And notice I just put absolute value on each one. That way, whichever one comes out negative, which would be this one, the absolute value would make it a positive value, and then I'd end up with a total distance versus displacement. The other way you can do it is, since we know that that first part of our interval from 1 to 4 is going to give me a negative value, right? That's what we determined right here. Our velocity is negative, so we're traveling in a negative direction. So we're going to get negative distance on that interval. Then when I do my calculation with the integral here, I just rewrote it by taking the opposite of v of t there. Right? because I know that's going to give me a negative value, so we'll throw in the negative just to counteract that. You see it done both ways. I don't care really which way you do it. Actually, I typically do it this way. I wrote this out initially, but I typically do it with the absolute value. I think that's because that way you don't even have to bother with the test strip if you don't want. All I need to know is where do I need to break my interval, right? Where is my velocity changing? Right? Where is it equal to 0? And I don't even need to know where it's negative or positive. So I just slap absolute value on each piece of it, and then that'll take care of itself. So either way, but you absolutely, as before, have to know where velocity is 0, so we know where to split our interval. After that, we're back to basic integration, right? So in this one, I went ahead and did the negative, so that when I found our antiderivative of v of t, right, which is the same antiderivative we found up here, nothing changes. Right? It's still like t cubed over 3 minus t squared minus at. That hasn't changed. But when you apply the negative, then I've got negative t cubed over 3 plus t squared plus 8t for that first interval. Right? So either way, either throw in the negative on the negative part to make it positive, or throw absolute value on each integral. I don't care which way you do it. Bottom line, though, is I need to calculate the distance traveled over each of those intervals, disregarding direction, so that we can find total distance traveled. And so then we're evaluating each of those intervals. So the first one over the interval from 1 to 4. Second one over the interval from 4 to 6 seconds. Right? And so again, that's calculation, plug in 4, plug in 1, plug in 6, plug in 4, and then do our calculations. And you end up with a total of 32 2/3 total meters. Right? And again, notice everything comes out positive here because of that negative counteracting the negative in the first interval. Here, without that, that first integral from 1 to 4 of v of t dt comes out to be negative 18. And the absolute value forces it to be positive, right? So we get the same values that we got on the other one. Yeah, so that's just whatever your personal preference is. Okay, but that, again, the main thing is there's a difference between displacement and total distance, right? So be careful of which one you're calculating. And don't forget your units. That's it for that section.